This video is about doing calculations that involve limiting an excess reactant through what is called a BCA method. BCA stands for before, change, and after. What I like about the BCA method is that it symbolizes time. Reactions are dynamic. There's a forward movement to them. The first time students see equations, they're typically in math class, and so there's equality to one side and the other, and so that's very static. In chemistry, there's movement forward. There is a beginning and there is an end. And so we use the directional arrow to symbolize that movement from beginning to end. Also, the unique thing about our reactions is that they react in a mole-to-mole ratio. So the amount of reactants are linked to the amount of products through a mole-to-mole ratio. And the BCA method really focuses on that stoichiometric connection of all of the species involved. Excess and limiting reactants, when you do those problems, they can get a bit cumbersome with how many different dimensional analysis tables are set up. And so BCA method really sets up everything at once. And so you can see what do you have at the beginning, how does it change over time, and then what do you have at the end? Once the reaction stops, what is present? Is there any excess reactant? If there is, how much of it? What about the products? All the products all at once, without trying to helps lays it out in a very organized way. BCA methods are also really good for titrations, whether it's an acid-base titration or a redox titration, which work on a mole-to-mole connection with how they're reacting in different ways. And then at the end, once it does stop, what is all present? What's in that reaction vessel? The BCA lays it out very nicely. It's modeled after the ICE tables for equilibrium. So if a student can really understand a BCA and the symbolism behind the signs that are used, when they get to reactions that are not just forward but also have an impact of reversibility to them, then when they get to an ICE table and they've already done BCA, it makes it a very smooth transition. And also about BCA is that it really does force a student to understand that when the reaction is over, after it stops, the amount of limiting reactant is zero. It's gone. There is no more left. And so that sets up and drives this BCA table forward. Here's a problem. If 26.4 grams of nitrogen gas were to react with 5.25 grams of hydrogen gas, what mass of ammonia gas would be produced and what mass of excess reactant, if any, would remain in the reaction vessel after the reaction stops? So we start with the equation. You have hydrogen and nitrogen, and they're making ammonia, and so we use an arrow to show that forward movement. Since we're talking about quantities of nitrogen and hydrogen and ammonia, it's very important that equation is not useful quantity-wise until we balance it, so you should balance it next. And you see that they have a 1 to 3 to 2 ratio, and understand that that's in a mole amount. Those are called mole ratios. What I also like to do is write down all the given in a column fashion. So underneath the nitrogen, you are told there are 26.4 grams of nitrogen. You are given that there is 5.25 grams of hydrogen. And then the unknown. So you're asked to find the mass of ammonia. So I like to put a question mark in the unit we need. And then you're also asked if there is an excess reactant, how much is left over. So some signs that this is a limiting reactant problem. When you are given two quantities of reactants, you need to check and make sure, is that the right amount? Now, the 1 to 3 ratio is not a mass ratio. It is a mole ratio. So masses of different substances are not comparable. They each have their own molar mass. Some are lighter, some are heavier. And so the 1 to 3 is a quantity, which a mole quantity is comparable. A mole of nitrogen is equivalent in quantity to a mole of hydrogen. So the 1 to 3 needs to be a mole. So step 1 right away is convert those masses into moles. So we're going to take each of the given masses over here on the left, divide by the molar masses, noting that nitrogen is diatomic as well as hydrogen. And we get 2 mole amounts. We have a certain mole of nitrogen now and mole of hydrogen. Now, what we need to check is that is the nitrogen to hydrogen a 1 to 3 ratio? Is the amount of hydrogen 3 times larger than the amount of nitrogen? If you can tell right away that it's not, then you go ahead and you can label the hydrogen limiting reactant. If you can't tell, or the numbers aren't as easy to see, 1 to 3 or 1 to 2, if it's a little bit more challenging, so then what you do is over on the side, you take the given amounts, and you check the limiting reactant this way. You put the given amount, 0.942 moles of nitrogen, versus the 2.60 moles of hydrogen, and you divide each respective given amount by their respective mole ratio amount. So the nitrogen should be 1 and the hydrogen should be 3. So when you divide those through, if you get the same numbers, then it shows you that proportionally they are using the right amount of nitrogen and hydrogen. So you divide them through and look at them, and you compare them, and you find that they're not the same number. The hydrogen is lesser, and so the one that is the lesser of the two is the limiting reactant. That's another quick way to identify what is a limiting reactant. And from then on, you label it, and then it's a limiting reactant that drives the rest of the reaction. As soon as it is gone, the reaction stops, and so we base everything that is made on the limiting reactant. If the hydrogen is a limiting reactant, then the nitrogen is going to be left over, and we call it excess. And so that's going to be your excess amount. And so now, once the limiting reactant is identified, we move into the BCA format. This is a BCA table. You'll see a column for nitrogen, hydrogen, and ammonia. I like to add in the double-sided arrow double line to break between the reactants and the products, so we know the left side is being used up, going to be making products on the right side. So there's a double-sided line there. That's also very similar in an ice table. The B stands for before, the C is change, and the A is after. And so we're going to symbolize time from top down. And when you do a BCA, when these change, when there's a reaction here, it's a quantity based, so it is only based on moles in a BCA. So only moles go in here. So we're going to take the given mole amounts, the 0.942 that we calculated before and the 2.60, and those go in the BCA table. So before the reaction proceeds, that's how much nitrogen and hydrogen we have. There is no product, and so 0 on the product side. As it changes, it's going to go forward, and so reactants are going to be used up and gone as products are going to be made. And so we use a negative sign for the loss of reactants over time and a positive for those that are gained. And when they change, we say they change in a stoichiometric way. Hydrogen to ammonia is a 1 to 3 to 2 way. So for every 1 nitrogen, you're going to need 3 hydrogens. And then when those bonds break and they rearrange, you're going to be able to get 2 ammonias out of it in quantity. We're not quite sure how much yet, so we're going to put an X in. So we know that whatever loss it is going to be, it's going to be stoichiometric. It's going to be a 1 to 3 to 2. And now we come to our after. The after row is a combination of the before and the change. So before, how much do you have? How is it going to change? And then that's what you're going to get after. So the before and the change are combined, and they will be the after. So we're going to write some expressions here. So the nitrogen, after the reaction's over, it's going to be whatever original amount we had, 0.942, minus some loss, and that's our after. Hydrogen is the same way, and then that ammonia is going to be, from a 0, we're going to add twice as much. And now this is very similar to an ice table if you're familiar with an ice. The thing that distinguishes this differently is not just that we're not using molarity, which is what we use in ice. We're using moles in a BCA. But then also understand that limiting reactant, after it is over, that amount goes to 0. This is going to be gone when the reaction stops. So after the reaction stops, that goes to 0. That's going to allow us to set up an expression. We're going to set up the 2.60 minus whatever loss it is, which is going to be all of it. It's going to go to 0. And so that's going to allow us to solve for x. So we rearrange, solve for x. Once x is found, this is the only variable we're using. And so it's the x that applies to the nitrogen and the x that applies to the ammonia. So we can plug that number in to those columns there. Nitrogen is now 0.942 minus the x loss, so 0.866. The ammonia over there on the right is double the x, and so you get 0.173. And then the important thing too, again, moles are only used in BCA tables, and so any number that comes out of a BCA table is also moles. So these are 2 mole amounts right now. And then our last step is we need to know masses. So I know mole amount of excess nitrogen. I know how many moles of ammonia I make, but I need to get those into masses. So then I'll just do a quick mole to gram conversion. So I'm going to be using multiplying by the molar mass. So nitrogen times, again, its diatomic mass. The ammonia is converted to grams by multiplying by its molar mass. So at the end I have 2.13 grams of nitrogen in excess, and I produced 29.5 grams of ammonia along the way.